This topic lesson 3. So this is called Redshift and the Big Bang. So in this lesson we're going to look at the evidence that scientists have observed and measured that support the idea of the Big Bang, and one of those pieces of evidence is called redshift. So in this lesson we're going to find out what redshift is, who first observed it, and how it supports the idea of the Big Bang. Now the first thing you need to do was, on the PowerPoint there's a small video clip of a car that's coming towards the camera and then passes the camera and goes away from the camera, and you have to describe how does the sound change when the car is coming towards the camera and going away from the camera. Well, the first thing we can say is that when it's coming towards the camera it gets louder, and that's sort of obvious. The car that's making the noise is getting closer, but also the pitch or the frequency of the sound increases. And then we can say that when it's going away from the camera, the sound gets softer and the pitch decreases. So you can just look at that clip again, make sure that you're able to see that. Now this effect with sound is known as the Doppler effect, and it's to do with the fact that with waves, as we increase the frequency of the waves, the wavelength decreases. So you need to fill in the spaces, so pause the video and check your answers. So check your answers. Next task you had to do was just a recap task looking at frequency and wavelength. And the first thing you needed to do was to draw a wave, to label the wavelength, add the unit, and define what frequency is. So the picture of the wave is shown here. On the y-axis you notice I've written displacement. This is how far the wave moves perpendicular to the direction of energy transfer. And on the x-axis I've got distance, and the wavelength is the distance between a point in the wave and the same point on the next wave. So it could be from peak to peak or trough to trough, or from the central equilibrium position to the same position. That's the wavelength. Frequency are the number of oscillations or complete waves that pass a point every second, and it's measured in hertz, written H-E-R-T-Z, or as a symbol, capital H, small z. In this task you need to draw two waves. You need to draw a wave that's got a long wavelength and say whether this has got high or low frequency, and then draw a wave that's got a shorter wavelength, and again, does this have a high or low frequency. So on the top we have a wave that's got a long wavelength, and this has got low frequency. And at the bottom we've got the wave that's got short wavelength, and this is high frequency. So you need to now fill in the gaps that are at the bottom, and it says for a wave moving at fixed speed. So check your answers. So for a wave moving at a fixed speed, at a particular speed, that typically you'll think of light moving in a vacuum. All electromagnetic waves move at the same speed in a vacuum, the speed of light. And when the wavelength becomes longer, the frequency decreases, and when the wavelength is shorter, the frequency increases. And that's easy to see actually from the equation, which says that speed is equal to frequency times wavelength. So if the speed is a number that doesn't change, then if I, for example, double the frequency, I need to halve the wavelength. Or if I was to increase the wavelength 3 times, I would have to decrease the frequency 3 times. The next task is to use the PowerPoint to look at what happens when we have waves that are produced by an object that's not moving, and then on the next page for an object that is moving. So in the first case we've got an object that we're going to say is stationary, and what we need to do here is draw how the waves spread away from this object. So this is what's called a wavefront diagram that shows typically the peaks of the waves as they move away from the object. So what we can see is that for the object that's stationary, it produces a wave, and the wave starts to move away in all directions. So we have this black peak for this wave that was produced some time ago, and it's spread quite far away from the object. But behind that there's the next wave peak, that's the blue one that was produced sometime later, and then the pencil coloured one, and then the red one. My diagram isn't obviously very good, yours would be much better I'm sure, but these are essentially circles around our stationary object. So what that means is that the wavelength, which is the distance between the peaks, is always the same. So the wavelength is always the same, and it is the same in front and behind the object. Okay, so if you imagine these are circles, it's better drawn obviously on the PowerPoint as well. So if you look again there, you see that the wavelength is always the same in the front and in the back. Now, just to put this together with the picture that's up here, what this is really showing is the wave moves out in peaks and troughs like this. So this is the wave, and it does this in all directions. So we have a peak and a trough and a peak and a trough and a peak and a trough and a peak in that direction, and so on. So the wave spreads out like this, and this wavefront diagram just shows us the peak for each wave. Okay, now we're going to look at the case where we have an object that's moving. So there's a typo there that should have said moving. So what we have in this case is we have an object that's moving in this direction. The movement is in this direction. So after it's produced the first wave, what will happen is when it produces the next wave, the wave that it originally produces is spreading out in all directions, but it's moving towards, along with the wave that's spreading out. So it will be catching up with this wave that's spreading out. Like that. And again, here's one that was produced earlier, and again, we're starting to catch up with that wave produced here. If I put in another one like this. Again, in the PowerPoint, there's an animation of this which shows this clearer. So what that means is that the wavelength on this side, so the wavelength in front of the vehicle, is shorter, so the frequency is higher because it's shorter than the wavelength behind the vehicle. You can see the wavelength behind the vehicle is very much larger. So this is why when the vehicle is coming towards someone standing here, they're going to hear the sound with very short wavelength, so the frequency will be very high. When the vehicle is moving away from someone, they're going to hear the wavelength as being very long, so the frequency will be much lower. So if it's coming towards you, you hear high frequency. If it's going away from you, you hear lower frequency. And this is what we saw in the video clip right at the start. So in the next task, you're going to summarize what we've looked at so far for the Doppler effect. So pause the video and check your answers. So what you should have is, if the object is stationary, then the frequency and the wavelength are constant. So whether you're behind the vehicle or in front of the vehicle, it's always the same wavelength. If the vehicle is moving, then if it's moving towards you, closer to you, the frequency is increasing and the wavelength is decreasing. If it's moving away from you, the frequency decreases and the wavelength increases. So this is called the Doppler effect, and it's what we call it, this effect for sound waves. But this also applies to light. Light is also a wave, and it's made up of different wavelengths and frequencies. And we can first of all think about how the colors of the rainbow relate to the wavelength and the frequency of light. So I want you to use the PowerPoint and check, finish labeling this diagram showing the spectrum of colors. So what we have is on the red side of the spectrum, this is long wavelength and low frequency. And by the way, we saw when we looked at electromagnetic waves, this means this is lower energy. So we've got long wavelength, low frequency for the red wavelengths. For the blue, violet, this is short wavelength and high frequency and higher energy. So red means that we have long wavelength, low frequency. Violet means we have short wavelength, high frequency. And remember, we're trying to relate this to this idea of when an object is moving towards you, the frequency increases and the wavelength decreases, and when it's moving away from you, the frequency decreases and the wavelength increases, and we can link this to the colors of light. First question we have is, what is redshift? So again, pause your video if you need to correct your answer. So redshift is the change, in the wavelength and frequency of light from an object that is moving away from us. The wavelengths are longer and the frequency is lower. That means, that is, they are shifted to the red end of the spectrum. So again, when we have that picture here, we see that they're moved towards the red end of the spectrum where the wavelengths are longer and the frequency is lower. So pause the video, make sure you've corrected your answer. So what happens is that when we look at galaxies, that are very far away from us, we see that the wavelength of light has increased. And if we see that the wavelength of light has increased, that means that the galaxy is moving away from us. Now, this was first discovered by someone called Hubble, and he noticed two things, and in this section you're filling in the two things that he's noticed, and again, pause the video to check your answers. Okay, now these were the observations that Hubble made, and he was able to draw three conclusions from his observations, and this is what you're filling in here. So once again, pause the video, check your answers. So these were his conclusions. Most galaxies are moving away from us. That's because we see redshift. The further away a galaxy was, the more redshift there was, which means the faster it's moving away from us. And he concluded from this that the universe is expanding. And to understand where that is, if you think about, if I had, I'm standing here, and there are two objects, A and B, A is 1 meter away and B is another 1 meter away. If the universe was expanding, so after, let's say, 1 second, each of those meters turns into 2 meters, then what we see is that now, after 1 second, A is 2 meters apart. So the speed that A has travelled at, it's travelled a distance, from my point of view, it's gone 1 further meter away in 1 second. So it's travelling at 1 meter per second. For B, what's happened there? Well, this has become 2 meters, but this has also become 2 meters. So B is now 4 meters away. It was originally 2 meters, now it's 4 meters away. So the speed of B is it's traveled 2 meters in 1 second. So it's traveling at 2 meters per second. So the object that's further away appears to be moving faster away from me because all of space is expanding. So this is what Hubble was able to conclude from his observations. Well, now the next thing that this suggests is if the galaxies are all moving away from each other, and one of the things that's important to realize is that in the previous discussion where we talked about redshift, we talked about the galaxies moving away from us. But we are not at the center of the universe with everything moving away from us. It's every single part of the universe. The space is expanding in every single part of the universe. So there's no center to the universe, and we'll come to look at the balloon model that'll help you to understand that. However, because the galaxies are moving away from each other at a great speed, this suggests that they were closer together in the past. And this model of the universe is called the Big Bang theory. It suggests that all the matter of the universe was originally in a very small space, and this space was very dense because all the material was there, and it was very hot. Now, to understand why this is, if you haven't already, watch this video that explains how to use the balloon model of the Big Bang to understand how the universe expands and why we see the galaxies moving apart. If you get a chance and you can get a balloon, you can try it for yourself. There's 2 experiments you can do. One is just to draw a wave on a balloon when it's not been blown up. And when you blow up the balloon, you'll see that as it blows up, the wavelength is stretched. So this is redshift. And when we deflate the balloon, the wavelength decreases again. Or alternatively, what you can do is draw some dots on a deflated balloon. These represent the galaxies. And when you blow up the balloon, you see that all the dots move away from each other. But the dots that are side by side, they move a little bit away from each other. But the dots that are on either side of the balloon, the distance between those increases by a very large amount. So the dots are moving apart, even though there's no center. All the dots that are on the surface of the balloon are all moving apart as the balloon is blown up. So the galaxies are moving apart at very great speed. This suggests that we're closer together in the past, which is called the Big Bang theory. So you need to write in here, what was the universe like initially, and what evidence do scientists have that support the Big Bang theory? So what we have is, what was the universe like initially? Initially, all the matter in the universe was concentrated in a very small, dense and very hot space. Since then, the universe has been expanding, and it's still expanding. What evidence do scientists have to support this idea? Well, firstly, the evidence from redshift shows that the galaxies are moving apart, and this is explained by the idea that space is expanding. And the second piece of evidence is something called cosmic microwave background radiation, and this is radiation that's been predicted that if the Big Bang happened, if this is how the universe started, it would release this type of radiation, and this type of radiation has been detected. Now, in this discussion of the Big Bang theory, it's important that you understand some of these terms that are used by scientists. They don't mean the same thing that the words mean in everyday English. So when people speak about theories, sort of in everyday, they have a theory about why something has happened in the news or why something is happening on a TV program. That's basically an idea that they've come up with. There's not much evidence for it, and it might be true or it might not be true. In science, a theory is not that. A theory is a model of the universe that explains, so first of all, it has to explain why the universe is the way it is. but it also is based on the observations of the universe and evidence from experiments. So a theory is a model that is backed up by all the scientific evidence. So examples are the theory of evolution by natural selection, or the atomic theory of matter, that all matter is made from atoms. Those models of how the universe works, we believe that those are correct because they explain and predict all the things that we see in the universe and the evidence that comes from experiments. However, if some new evidence is discovered, that means that the theory may have to be changed or a new theory may be needed. And this is something that was discussed in more detail in topic 4, which was to do with atomic structure, where we saw that the model of what the atom looked like changed from its initial idea with Dalton to the plum pudding model to the new nuclear theory of the atom that explains the new evidence from the discovery of electrons, protons and neutrons. So when new evidence is discovered, the theory may need to be changed, or even a completely new theory may be needed. So here there are sections for you that to fill in, that you can look at the things that I put in, but particularly the last section. What questions do you think you'd like to be able to ask or explore about the universe? That's purely for you to think about. What would you like to discover about the universe? So some of the recent discoveries that there have been, one of the most important is the discovery of other solar systems. Sometimes these are called the exoplanets. So these are planets going around other stars. So this is something that people thought might be the case, but there is now, these things have actually been measured and detected going around other stars. So it means that of all the billions of stars in our galaxy, many of them have planets, and some of those planets may even be similar to the Earth. Other things that have been discovered are the size and the age of the universe. So scientists have been able to look back to almost the start of the universe to see what age it is when it started. Other things are things like how stars work. How is it the sun can provide all the energy that we need? And so this is linked to something called nuclear fusion, which appears in the electricity topic, the atomic structure topic, so topic 4, to do with the idea of using nuclear power, fission and fusion in reactors. So these are some of the things that have been discovered, and obviously there's been lots of small discoveries, individual discoveries about the different planets from all the probes that have been sent to the planets within our solar system. There's even been robotic probes sent to investigate comets and to land on comets. So there's lots and lots of discoveries recently, and the rate that these things have been discovering is increasing as our technology becomes better. However, there are some things that we still do not yet understand. And the second thing you needed to talk about, what is dark matter and dark energy? And this often appears in news programs where they're talking about some of the new scientific experiments being looked at. And the first one, dark matter. So one mystery about galaxies is how they're held together. And this is an idea that they're held together by some unknown material that holds the galaxies together. Because without dark matter, because the stars are moving at very high speeds, they would fly apart. The galaxies wouldn't stay together as a collection of stars. So something else is holding the galaxies together. We don't know what that is, and this is called dark matter because it doesn't emit any electromagnetic radiation. So, for example, it doesn't emit any light. The second thing is dark energy. And in some ways, this is even more mysterious. One of the things I've said already is that the Big Bang model suggests that the universe expanded and is continuing to expand. But with recent observations, they discovered that the galaxies are accelerating. So they're not just moving away from us, but they're actually moving away from us faster. So therefore the universe is expanding at a faster rate. So it's not just getting bigger, but it's getting bigger faster. And this is thought to be caused by something called dark energy. But still, scientists are still investigating what that might be. Some of the other questions that I put to think about are: what will happen to our universe? How will it end? Will it end? Will it just continue expanding forever? Or will it eventually start to collapse again? We don't know. Is there only one universe? Or are there many universes? So is it a single universe, or are there many universes? And we call that the multiverse, and there are reasons why there is some evidence to support this idea. And then possibly one of the most interesting questions is there any extraterrestrial life, either within our solar system, perhaps on some of the moons around the gas giants, or in these solar systems that have been discovered on these exoplanets? And within that extraterrestrial life, certainly if it exists elsewhere in the solar system, it's likely to be single cell type organisms. But then the question, of course, is there intelligent life, such as similar to human life, anywhere else in the universe? In this last section, this is for you to fill in with any questions, any ideas, things that you'd like to find out about space.